Welcome back, Physics 11, to our last video of the year for this unit. So this is the plan that we're going to be doing for the next 2 weeks. These notes are a tiny bit longer than our typical notes, but this is for 2 weeks worth of work. So we're going to be covering two topics today in our lesson. One of them is going to be electromagnetic radiation, and so that's talking about different forms of light. So when we typically think of light, we think of just the visible spectrum, what we can see, the rainbow, but there's obviously a lot more to electromagnetic radiation that our eyes can't detect. So if we want to see what the entire spectra is, so if we go from the longest wavelength to the shortest wavelength, we'd be going in this order here. So we typically, there's a lot of mnemonics that you'll hear for this spectrum here. So radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays. One of the ones that I like to use is raging Martians invade Venus using X-ray guns. There's some other ones that are out there, probably not as appropriate, so this is a good one to use, and it just tells you what the spectrum is. So radio waves are the longest type of light that is part of the electromagnetic spectrum, and gamma rays have the shortest wavelength. They're also the most energetic. So these ones here, ultraviolet X-rays and gamma rays, these are all the ones that are powerful enough. So there's enough energy in these types of electromagnetic waves that they can actually cause damage. So gamma rays are a form of radiation that comes from places like Chernobyl. So yeah, gamma rays will definitely give you cancer. X-rays in large enough doses can be cancerous. Ultraviolet, you know, people who spend too much time in the sun, they're getting UV damage, which could also be eventually harmful, but not as harmful as these other two. Still, put on sunscreen, right? But any of these right here, these are not harmful. So millimeter waves fall under this one here. So if you've heard anything about 5G, these are way on the other end over here. These are not harmful at all. Okay, so EM waves, the type of wave that they are, these are transverse waves. So we talked about this last week, transverse waves being the waves that sort of oscillate perpendicular, draw that very well, oscillate perpendicular to the direction of motion. So as the wave is moving left to right, they're oscillating up and down. That's what a transverse wave is. Now the speed of light depends on the medium. So medium is essentially just a substance that light is traveling through. And the more optically dense some material is, then the slower the speed of light is going to be in that. Now, one thing to note is that it doesn't matter if it's gamma rays or radio waves, they're all traveling at the same speed in a vacuum. And the speed of light in a vacuum is 3.00 times 10 to the 8 meters per second. So this is the speed limit of the universe. So nothing can travel faster than this in a local distance. Okay, so yeah, this is the entire spectrum here. This is kind of giving you, if you look at this here, look at your notes. These have the longest wavelength, shortest wavelength. These have the highest frequency over here and lowest frequency. And we can see that in this chart here. So very small frequency, very high frequency, very long wavelength, very short wavelength. These could be a kilometer long. These are like femtometers or picometers. They're very, very small. Okay, so let's try doing this. We've got a couple of practice questions here. So question 1 and question 2. This is just asking us how long light takes to pause the video here and give these questions a try. Okay, so if you're back after trying these two questions, let's give this a go. So you'll notice here this is in kilometers. So if it's this many kilometers, that means we can multiply by 1,000 to get the number of meters. So how long does it take us to reach it? Well, we know that speed equals distance divided by time. In other words, time equals distance divided by velocity. This is going to be 1.5 times 10 to the 11 meters, and we're going to divide this by 3.0 times 10 to the 8 meters per second. And this is going to give us approximately 500 seconds. Now, if you calculate this, which is about 8.3 minutes. So what's interesting is if the sun were to disappear somehow, we wouldn't know about that for about 8 minutes. If anything happens in the sun, we're seeing that 8 minutes later. Now, Alpha Centauri is the nearest solar system to ours. It's this many kilometers away, 4.07 times 10 to the 13. So how long would it take light to travel from Alpha Centauri to us? Well, same formula here. Time is going to be the distance divided by velocity. This is going to be 4.07 times 10 to the 10 to the 16 meters. I fell for the same trick. And we're going to divide this by 3.0 times 10 to the 8 meters per second. And if you go through your calculation here, you'll find this is approximately 4.3 years. Now, you may have heard the term light years before. So 1 light year is just how far light can travel, traveling at 3 times 10 to the 8 meters per second for 1 year. How long or how far would that light be able to travel? So Alpha Centauri is 4.3 light years. It's the closest other solar system to ours. Anything that happens at Alpha Centauri right now, we wouldn't be able to hear about it for another 4.3 years. That's how long it would take for it to get to us. Okay. Now, this is probably old information. Hopefully, it's old information for most of you. This is about what we actually see as visible light specifically. So when we look at visible light that's white, we're actually seeing a combination of all of the colors of the rainbow. And you probably remember this: red, orange, yellow, green, blue, indigo, and violet. That's our rainbow. Uh, you may have heard the mnemonic of Roy G. Biv. Do you remember that, perhaps? So different colors of light, they are going to have different frequencies and wavelengths. And in fact, these will always have a constant relationship. So remember that we talked about in the previous lesson, we talked about how the speed of a wave is the frequency multiplied by a wavelength. Well, in this case here, all the different parts of the electromagnetic spectrum, all the different colors, radio waves, gamma rays, etc., these all have the same constant speed. And so if the frequency is going to double, the wavelength is going to be divided by 2. So these will have an inversely proportional relationship. So the longer the wavelength, the shorter the frequency, and vice versa. Now red happens to have the longest wavelength, and violet has the shortest wavelength. Now, where does this light actually come from? Well, this light, visible light, as well as all other forms of light, actually just come from energized matter. So I'm not going to go into too much detail, but essentially we know that in an atom there's the nucleus and there's the electrons that live in shells or orbits around around an atom. So as these electrons absorb energy, they will jump from one shell to another. But they don't want to live in a shell that's kind of an it's considered unstable if they have more energies in the lowest possible setting. So once they have moved up, a short while later, they will drop back down. Now, when they drop back down, they're going to release light in the form of a photon, and it will have the exact same amount of energy that it did to absorb it to go up a shell. So whenever we see light, it's actually coming from an electron that's dropped down to a lower shell. So after energy is absorbed by matter, it gets re-emitted. That's what we're saying right here. And each element emits very specific frequencies or wavelengths of light, and this is known as their atomic spectra. And essentially what this means is that for different atoms, where these shells will be located will be slightly different. So this might be a hydrogen atom, but a helium atom will have different distances for their shells. So it won't be, if this distance here only allows it to absorb certain frequencies, well, this distance here will be different for different atoms, and so they won't be able to emit the exact same light. They'll have their own specific frequencies. It's kind of like a signature for each type of matter. So what is this good for? Well, if we look at this picture on the left here, we're showing two different atomic spectra. So this right here is what's called an emission spectra. So this could be used for trying to look at stars. So to find out what stars are made of. So for example, if we look here closely, this is the signature for hydrogen. So hydrogen will emit photons of this wavelength, this wavelength, this wavelength, and this wavelength. Mercury will emit this wavelength, etc. So all these different ones here, and neon will emit these ones here. So if I were to look at a star and I were to see something that looked like this, I would see these lines plus these lines here and this line and this line. Well, I could look at this one here and say, well, this particular star, this is kind of an unusual example here, but this particular star has all the lines from the top and all the lines from this middle one here. So this particular star, this particular substance must have both hydrogen and mercury. So we can look at these different spectra and say, okay, well, those 5 lines, those represent a star that has hydrogen. Those 7 lines represent a star that has helium. So we know that this one has a certain amount of hydrogen, a certain amount of helium. This bottom one here, this is known as an absorption spectra. And so this absorption spectra is essentially used to determine gases that are in between something. So let's say, determine gases between stars and observer, or us. So what's happening here is, let's say there was a gas cloud, so a giant gas cloud out in space, and there's stars behind it. Now, as the stars are shining through, what you're seeing is that all the light from the previous stars made it through, except not this part, this part, this part, and this part. So what that's saying is that as the light was coming through here, it goes to this cloud here, and when it gets here, all the other light makes it through except hydrogen, the lights or the lines indicating hydrogen. And the reason for that is that this gas is made up of hydrogen. So as the light goes in here, it's going to be absorbed by the hydrogen, then it's going to be shot out in different directions. And so it doesn't quite reach our eyes because it's being scattered. Now, just like I said before, when the light goes down here, it's going to emit a certain frequency of light. That also means that hydrogen can only absorb a certain frequency of light or a certain wavelength of light. So hydrogen can only absorb that, meaning that if this cloud looked like this, only hydrogen was being absorbed. The other elements weren't necessarily present, and that's why they weren't absorbed. So just some interesting information for you there. Okay, moving on to the main topic, which is the topic that we're also going to be doing a lab on today, and that's on the unit of refraction. So as I said before, wave speed does depend on the media that it's traveling to. So what happens when waves travel from one medium to another? So let's look at an example where we're having waves going from uh, deep water into shallow water. So let's say along this line here, everything to the left here was deep water, and everything along here after this line was shallow water. As we have waves that are moving part here, they're moving in this direction here. So these are the tops of the waves that we're trying to picture here. So these waves are kind of evenly spread apart. Now once they get to this line here, they slow down. Now as they slow down, you'll notice that this part of the wave, so we're kind of trying to picture these waves moving in this direction here. So what we can see is when this next wave here, when this wave hits this line here that goes from deep to shallow, this part here is going to slow down first. And then this part's going to slow down a little bit later, this part's going to slow down, etc. So what that results for us is that the wave is going to actually bend. So this part will be going the slowest for the longest period of time, and this part will still have been going full speed up at the top. So this part's going full speed, but this part's slowing down. And the lower they are on this particular wave here, it means the longer they've been going for at a slower speed. And so what you're going to end up getting is these waves that are moving in this direction overall. Now you'll also notice that they end up being a lot closer together. So two things are happening. One, it's changing direction, and two, the waves are getting closer together. So whenever waves travel perpendicular to a medium, so that is if this black line was going straight up and down, you can see that they wouldn't necessarily bend if they were traveling perpendicular. But the velocity would decrease, or the velocity in general going from one to another is going to change. But is the frequency going to change? So if we take a look here, every second, let's say, imagine one of these waves is hitting this black line here. So every second, a wave is hitting this black line. So every second, one wave is going to be leaving this black line. So has the frequency changed? If there's 10 waves hitting it per second, there's going to be 10 waves leaving it per second. So in fact, the frequency stays constant. So if the velocity is changing, but the frequency is constant, that means the wavelength also changes, right? Because we have this formula, V equals F times lambda. So if this is the same and frequency goes up, for example, wavelength has to go down. If frequency goes down, wavelength has to go up. So if one changes, the other one will change. So when waves are not perpendicular, they're also going to bend. So we see these two phenomenon happening. Regardless of when it goes from one medium to another, it's always going to change its speed and change its wavelength while the frequency remains constant. But if it's not perpendicular, then it's also going to bend. So those are the two things that are going to happen. And that bending is what we know as refraction. So this is bending of waves as they change medium, as they change media. Okay, and optical density is what I mentioned on the previous page, and this is how difficult it is for light or for waves to travel. Basically, it's an indication of how much it's going to slow down. So if it slows down a lot, that's something that has a high optical density. If it slows down just a little bit, then it has a lower optical density. So let's look at an example here. So we are going to actually get into calculations soon. Let's look at an example here. And so when we shine a laser into a piece of quartz, we're going to notice that that laser is going to change direction as well. It's going to bend. As it's going into something that's more optically dense, it's going to bend. And we have a few angles here that we'll identify just for the purposes of knowing the vocabulary and being able to do the calculations. So this is called the theta I, or angle of incidence, and this is theta R, or angle of refraction. And the angles you'll notice are always measured from what's called the normal line. So this line that's perpendicular to the surface of the material is known as the normal line, and the angle of incidence is the angle between incident ray or incoming ray and the normal line. Right, so here's the incident ray, here's the normal line, the angle between them, that's the angle of incidence. And the angle of refraction is going to be the angle between refracted ray and the normal. Okay, so here's the normal line, here's the refracted ray, and that's going to be the normal line. Now, one thing to note here, just to add this to it, if we were to continue this, we would still have the same rules that would apply to us. So we would call this, we would still have a normal line going from one medium to another. It doesn't have to always be going from less to more dense. So this is still a normal line, and this would, but what would this angle on the inside here be? So this angle here, this would now be the angle of incidence. It's the one before changing media, and this right here would be the angle of refraction. Okay, so the angle of incidence is the one before it changes media. The angle of refraction is the one after it changes media. So it doesn't have to be always the one that's outside of a glass block, for example. Okay, now I've given this example here, so this deep and shallow water, and we can see how the waves change here. Another example that might help out, and and this is how it was explained to me when I was taking science back in the day. One way of looking at this as well to figure out which way the direction of light is going to change is thinking of it this way. Let's say I'm driving in my Jeep, and this is the direction of my wheels before I'm changing media. So let's say this is pavement or cement, and this is mud after here. And this is a top-down view. This is where my four wheels are. Now, if this Jeep is traveling in this direction here, when it hits the mud, this wheel here is obviously going to hit the mud first. And this wheel here is going to slow down. So after it hits the mud, then this wheel is going to be going much slower, but this wheel is still on pavement, so this wheel is still going to be going faster. So if the left wheel is slower and the right wheel is faster, that's going to result in this changing direction. So what we're going to find is after it's reached the mud, this isn't a very good drawing, after it's reached the mud here, what you're going to find is that, again, the Jeep will have turned slightly to the left as it goes into the mud. I didn't really draw that very exaggerated, but nonetheless, you can see that hopefully this kind of makes sense. If you're picturing yourself driving into some place that's more difficult to drive through, just like light that's traveling in an area that's more optically dense, when it hits that optically dense substance, the side of it that's closest to it is going to slow down more, which means it's going to turn in that direction here. Okay, so we can calculate this now. We finally have a formula to work with. I know we all like dealing with formulas. We're physicists. And this is the formula that we have for determining uh, the angle that it's going to bend at. So this should just be N1. So N1 sine theta 1 equals N2 sine theta 2. So N is what's known as our index of refraction. So this is just a number that represents how much the light is going to bend, or another, actually more accurately, is telling us how much the light is going to slow down. This is our angle of incidence, and this is our angle of refraction. Okay, and I'll give you a few examples here. So for a vacuum, n is 1. That's the absolute fastest that light travels in a vacuum. Now, light travels just slightly slower in the air, so we have an index of refraction at 1.0000 or 0003. So it's telling us that it is not very difficult for light to travel through air. Water is 1.33, ethanol is 1.36. Same for these here, and 1.61. And for diamond, it's extremely high. It's 2.42. And this actually ties into the reason why people like diamonds as jewelry. And we'll see this more here. You can think about this and the next page when we talk briefly about angle of, or critical angle. And we'll see how this kind of plays into it in terms of reflective. Okay. So based on what we're seeing in this diagram above, and this idea of the Jeep driving through different substances, when we have light traveling from less dense to more dense, as in air to glass, for example, it is going to slow down, and it's going to bend towards the normal. So you can see here, the angle of incidence was larger here and smaller here, meaning it got closer to the normal line. When it goes from more dense to less dense, it is going to speed up. So it speeds up and bends away from the normal. So you can see it here. This angle of incidence is quite small. This angle of incidence is quite large. And you'll also notice here, I tried to draw it this way, when you have something going through a block, it's going to end up traveling out the same direction as it traveled in. It doesn't work that way for a prism if it's triangular, but for a square block or rectangular block, it doesn't actually overall change the direction of the light. Whatever angle goes in the block is the same angle that goes out of the block, which is why when you look through your plane of glass, if you have a glass window, it's not going to look drastically different. It's just going to be shifted over a tiny, tiny amount. Okay, so a couple more questions here. So again, one more time, please try and pause the video and answer these two questions here and here, and then we're going to have just a few more quick notes for the video. All right, well, hopefully you have taken the time and you've tried to do this for yourself. So let's take a quick look here. So I'm going to draw the diagram first. That's my first step. And this is saying that the angle of incidence is 15 degrees. So it strikes the block at an angle of 15 degrees. So here's my normal line. And the angle of incidence here is 15 degrees. Now, when it hits something that's more dense, it is going to go towards the normal. So this new line here will be bent slightly this way here, and we're trying to find out this angle of refraction. So we're going to go and use Snell's law, and so that's saying that n1 sine theta 1 equals n2 sine theta 2. You could use, instead of 1 and 2, you can use I and R for incident and refracted, but that's fine either way. So in this case here, we're talking about going through air. So if we wanted to be specific, we could say 1.0003, but to be honest, I think it's fine just to use 1.0 for the number of significant figures here. So 1.0, that's the incidence or the index of refraction of air. We're going to multiply that by sine 15, and this is going to equal N2. Now this is quarts. Quarts is 1.54, and we're going to try and find out what this angle of refraction is. So let's try and calculate this ourselves here. So what we have is, make sure I'm in degrees. So sine of 15 times 1, so I'm going to leave that, that's fine. I'm going to divide this by 1.54, and so that means that sine theta r is going to be equal to 0.168. Now we need to take the inverse of this value here, and that's going to give us our angle, which we'll find theta r is 9.7 degrees. So theta r equals 9.7 degrees. Okay, what about this? Now this is going from underwater into air. So this is going to be my water here, and it's traveling from underwater, and it's going to be reaching the angle, or actually what it says here, when it travels in the air, the angle is 65 degrees. So that means for our light here, this was 65 degrees. And we're trying to find out what this angle is going to be. Now, if it's going from the water to the air, it's going to speed up, and that means that left tire of the Jeep, so to speak, is going to speed up first, so that means it's going to turn to the left. That means it must have been traveling at an angle like this, and we're trying to find out what is this angle of incidence here. So we've got our diagram. Now let's try and calculate this. So n of the incident angle times sine of the, or sorry, n of the incident index of refraction times the sine of this angle here, which is what we're trying to calculate. This is going to be equal to n2, so this is the n of the air. I'm going to just change this to water and air, and times sine of 65. So we know what n of the water is, we know n of the air, and we know sine 65. It's just this data that we don't know. So let's try and calculate this here. So n of the air is going to be 1.0003. I'm just going to use 1 times sine of 65. That gives me 0.906. I'm going to divide this by the n of the water, which is 1.33, and that gives me sine theta I equals 0.68. The inverse sine of that function. And I have n of w is 43 degrees, we'll call it. Or sorry, sine, so theta of the water equals 43 degrees. That's what this angle here is, 43. Okay, just two quick things to teach, and then we'll be done for the week. So index of refraction is this formula here. So the n that we have is c divided by v of that n. So this, what this means is n is the index of refraction. C is the speed of light. And v, or vn, is the speed of light in the substance. And I guess what's implied here is this is in a vacuum. Okay, so the speed of light is the maximum speed of light. That's the 3.0 times 10 to the power of 8. And Vn is the speed in that particular substance. So what is the speed of light in water? If you can pause the video one more time, give this question a try. All right, and if you're back, here we go with this last question for us. So we know this is our formula here. N equals C over V, or Vn, and we're trying to solve what is Vn. What is the V of this particular substance, in which case it's water. So if we rearrange this equation, we know the V in the water is going to be C divided by N. This is going to be 3.0 times 10 to the 8, and we're going to divide this by the N of water, which is 1.33. This gives us 3 times 10 to the 8 divided by 1.33 gives us 2.26 times 10 to the 8 meters per second. So that's how fast light travels in water. Okay, so just to give you a quick heads up about our lab for the week. So I want to show you this. This is our lab for the week, and this is talking about talking about refraction here. And we can see here with the lab, you'll have a protractor, and you'll be able to measure these angles here. And so this is just roughly what you're looking at here. You can see again, in each case here, this is going from water into air. We're going to see that it's going to bend as it's going from more dense to less dense, it's going to bend away. So we're going to see this angle of incidence here and this angle of refraction at the bottom are going to be different. The angle of incidence will be smaller. If we were to flip these around, then it'd be bending away like we've seen in the previous example. Now, I want to show you one other quick demo, which is this one here for total internal reflection, which is our last quick topic. Take a look at this video. He's got a laser shining through a bottle of water, and he's going to poke a hole in the bottle here to allow water to travel, and watch what happens to the laser as it goes. Okay, so what we're looking at here is a phenomenon known as total internal reflection. So we know that when light passes from a more dense to less dense medium, it refracts away from the normal. So I'm going to show 3 different examples here. So this is an example of refraction. Let me zoom over here. So this is just normal refraction. Light goes out of the water, bends away from the normal. So another example of that would be, what if we were to increase this angle just enough? We can see here, this is the initial angle here. I'm going to increase the angle. So what happens if I keep increasing this? Well, this line here is going to keep moving further and further and further down until eventually I'm going to get to an angle here. We call this the critical angle, where the light is actually going to be reflected or refracted 90 degrees. So this is what's known as the critical angle. And if we increase this even more, what ends up happening is the light reaches here and actually is reflected back into the water. And this will essentially act just as a mirror. So this angle and this angle should be the same. I didn't quite draw them exactly perfectly. If we go back to this diagram over here, we can kind of see this a bit better here. So if we look over here, what's happening is as I move forward, this line is getting smaller and smaller and smaller and smaller and smaller until eventually somewhere around there it's at 90 degrees. So there's this perfect angle where the light just gets exactly to that line right there. I can't really go any closer. So we can see here, this is somewhere around 50 or 49 degrees is where this ends up having this total internal reflection. If you've like ever worn a waterproof watch in a bathtub, for example, you can see this as well. If you turn your wrist away, eventually there comes a point where you can't see your screen or can't see your watch anymore. So you can see this with things that are glass underwater. So let's try and do a few quick calculations, and then we'll call it quits for the week. So we can see that if it's large enough, the angle of refraction will be parallel to the medium boundary. This is known as the critical angle. And so this is the angle, sorry, I should say angle where the angle of refraction equals 90 degrees. So it's perpendicular to the normal line. And total internal reflection occurs when theta incident is greater than the critical angle. So if you're ever increasing this angle, so this angle here is greater than this angle here, then you're going to get this total internal reflection. And what you saw with that laser beam is exactly that. The angle was small enough that it was able to bounce back and continually bounce back and forth along the tube. The same thing happens with fiber optic cables. This is a fiber optic cable. As long as the angles are coming in at a steep enough angle here, it's just going to keep bending back and forth and back and forth. And that's how we can communicate with fiber optic cables. Same exact idea. So let's figure out what that critical angle is going to be. So the trick to this is recognizing we can still use the same formula. So n incident sine theta incident equals n refracted times sine theta refracted. The difference here is that sine theta refracted is going to be 90 degrees. And we should hopefully remember that sine of 90 degrees is just 1. So we're trying to find from water into air. So water is the incident, air is the refracted. That means we have sine, the critical angle is going to be the refracted substance, which in this case is air, which I'm just going to leave as 1.0. We're going to divide this by the incident, which is going to be 1.33. So if we have 1 divided by 1.33, this is the sine theta, and that means that theta is going to be 48.8 degrees. Theta equals 48.8 degrees, which matches up pretty well with what we saw on this one here. Somewhere around 48 or 49 degrees, this stops refracting or reaches around 90 degrees for the incident of refraction. Okay, so that's our video for the week. Please feel free to come by office hours if you have any questions, and otherwise enjoy the rest of your week. Thanks.